Welcome to this explainer. Right now, we're exploring an absolute frontier where two of the most disruptive technologies of our time are essentially colliding. We're talking about researchers building a very real mathematical bridge between state-of-the-art AI and the incredible, honestly almost sci-fi potential of quantum computing. So what happens when you run today's most powerful AI on tomorrow's quantum computers? Well, let's dive right into this fascinating question. We're looking at a truly groundbreaking paper today that successfully translates classical AI architectures, specifically vision transformers, into natively quantum circuits to analyze complex data, like medical images. It's a massive leap forward, and to really understand how they pulled this off, we're going to have to break down the mechanics.
Here's our roadmap for the explainer. First, AI meets quantum computing. Then, the vision transformer explained, building quantum tools, the three quantum architectures, testing on medical images, and finally, the quantum advantage.
Section 1. AI meets quantum computation, a new optimization space. For years, scientists have been trying to leverage quantum computation to provide powerful new tools for classical machine learning algorithms. But the big hurdle is, how do you actually feed data into a quantum state? Well, the answer lies in parameterized quantum circuits. By loading data into these circuits, the AI can explore vastly higher dimensional optimization spaces than classical computers could ever dream of handling. So the crucial point here is that by using natively quantum properties, like orthogonality, researchers can create highly scalable tools designed specifically for NISQ, or noisy intermediate-scale quantum hardware, which, of course, is the hardware we're working with today. Moving on to Section 2. The vision transformer explained, the classical baseline. To truly appreciate this quantum breakthrough, we first need to quickly ground ourselves in how classical vision transformers currently process visual data. Because when an AI looks at an image, say a picture of a dog, it doesn't just swallow the whole picture at once. Instead, it pre-processes it by dividing the image up into small, manageable squares, which we call patches. Those patches are then fed through several transformer layers to extract the meaningful features, basically piece by piece. But think about it. How does the AI actually know which pieces of the image are the most important? It uses what's called an attention mechanism. Instead of just looking at isolated pixels, this mechanism is what allows the neural network to consider the entire global context. It literally learns to weigh how much attention each individual patch should pay to the rest of the image. Now, the real heavy lifting of modern AI lies in the math behind that attention. Take a look at these trainable matrices, denoted by V and W. These matrices are mathematically learning the relationships between the patches. W is the one figuring out the attention coefficients, like exactly how much patch A cares about patch B, while V extracts the actual features. All right, Section 3, building quantum tools, translating the math. Having established our classical baseline, the big question is, how do we take those fully connected classical mathematical layers and actually translate them into quantum operations? To pull this off, the researchers had to design custom quantum tools, specifically the pyramid circuit and the butterfly circuit. These are trainable quantum orthogonal layers, and they perform complex operations right on the encoded quantum states. The butterfly circuit is particularly highly expressive. It uses a logarithmic depth, which makes it just incredibly powerful for processing these complex attention mechanisms. But as we know, quantum computers today are notoriously noisy, so they also introduced the X circuit. This specific architecture requires a much smaller number of gates and uses nearest neighbor connectivity. It's honestly a pragmatic, brilliant design choice that makes it perfectly suited to run on the imperfect, noisy quantum hardware we actually have access to right now. Section 4. 3 quantum architectures, scaling the complexity. So, armed with these new quantum data loaders and orthogonal layers, the researchers didn't stop at just building one model. They actually invented 3 distinct quantum transformer architectures. Let's see how this builds progressively. First, the orthogonal patchwise network. Second, the quantum orthogonal transformer. And third, the quantum compound transformer. We're going to step through these, going from the first, which closely mimics classical transformers, all the way to the third, which exhibits some wildly powerful native quantum characteristics. First up is the orthogonal patchwise network. This one's definitely the simplest of the 3. It essentially acts as a trivial attention mechanism. In its circuit diagram, each image patch is loaded individually, and it only pays attention to itself using a trainable matrix V. So it's a great baseline to start with, but it obviously doesn't take full advantage of the global context.
Now, stepping up in complexity, we have the quantum orthogonal transformer. This model actually calculates the interaction between different patches. It mimics the classical attention layer we looked at earlier, but it does it utilizing Hamming weight-preserving quantum circuits, meaning it computes the attention coefficient between patch I and patch J right there natively on the quantum hardware.
And finally, we get to the crown jewel, the quantum compound transformer. This is where things get truly quantum. Instead of computing these patches individually, it loads all the patches into a quantum superposition at the exact same time. Then, it applies a single higher-dimensional compound matrix operation to all of them at once. Doing this kind of math on a classical computer is just incredibly hard and resource-intensive, but on a quantum circuit, it's literally natively designed for it. Moving to Section 5, testing on medical images, proving the theory.
Okay, so theory and high-level math are great, but does this actually work on real-world problems? The researchers obviously had to prove their architectures could handle real data, so they put them to the test using MMNST, which is this massive collection of medical image datasets. Think X-rays, ultrasounds, that sort of thing. And the results? Honestly, they're astounding. The quantum architectures competitively match the classical baselines across the board. But even better, on 7 out of the 12 datasets, the quantum transformers actually beat the best-in-class classical benchmarks. They genuinely prove that it works.
Section 6, the quantum advantage, why this matters. Now, you might be asking yourself, if the accuracy is somewhat similar, why go through all the trouble of inventing complex quantum circuits for this? Why not just stick to our classical AI? Well, this right here brilliantly illustrates the ultimate payoff. To analyze these medical images, the classical vision transformer required 512 trainable parameters. The quantum compound transformer, it needed a mere 80 parameters. 80. That is just a staggering reduction in computational bloat. But what does that massive parameter reduction actually mean for us practically? Well, it means a heavily reduced risk of overfitting, which is where an AI just memorizes data instead of actually learning the underlying patterns. It also promises asymptotic runtime advantages, meaning it's going to scale incredibly efficiently. And because of the quantum orthogonal layers they used, it shows really strong potential to be completely immune to barren plateaus. If you're familiar with deep learning, you know that's a notorious problem where training just abruptly grinds to a halt. And just to prove this wasn't all just some theoretical computer simulation, the researchers took their transformer and ran it on actual physical superconducting IBM quantum computers. They tested it for up to 6 qubits using decomposed logic gates, and they achieved highly encouraging, really competitive accuracy. We're talking real code running on real quantum metal. Of course, we do have to stay grounded here. As the researchers themselves note, these findings are a promising yet preliminary step. Current quantum computers are still quite small and definitely noisy. We are going to need further empirical validation as the hardware scales up. But still, it is an absolutely incredibly exciting first step for the future of highly efficient, scalable quantum machine learning. Which leaves us with a pretty thrilling question to ponder as we wrap up this explainer. If these quantum transformers can achieve state-of-the-art medical image analysis today using just a handful of noisy qubits, as our quantum computers scale up to hundreds or even thousands of qubits, what other classical limits will these amazing architectures shatter next? The fusion of AI and quantum computing has officially begun, and it looks like the optimization space is wide open. Thanks for exploring this with us today.